Okay, next we consider the binomial distribution. Binomial distribution can be considered as a sequence of Bernoulli random variables. Okay, for example, let's consider flipping a coin n times. Flip a coin n times. So we can have either head or tail. So when we get head, the Bernoulli random variable has a value of 1, for example. And when we get a tail, the Bernoulli random variable has the value of 0. Okay. Then, out of n flips, how many times we get heads? Okay. So this number of heads is a random variable. Okay. Number of heads out of n flips. Okay. So how do we calculate this? And we are not interested in the order of appearance of heads. Okay. We just care about the number of heads out of n flips. Okay. So this means if we flip coins n times, there are how many combinations of getting k heads? So k is k. And okay, so since this is a Bernoulli distribution, we have probability p and probability q, which is 1 minus p. Okay, this probability is given by this formula. So, n factorial by k factorial n minus k factorial. So this is the number of combinations of having k heads out of n flips, and times p to the power of k and q to the power of n minus k. Okay. So why is this? Because, okay, let's consider a special case. So just consider first k flips are all heads. Okay. And the remaining n minus k flips are all tails. Okay. What is the probability that this particular sequence is obtained? So the probability of this is, getting a head in the first flip is p, and the probability of getting a head in the second flip is also p, and so on. So p continues. And then probability of getting a tail in this particular flip is q. So this continues, q. And all these flips are independent of each other. So that joint probability distribution is obtained by just by multiplying all these probabilities. So that will be p to the power of k and q to the power of n minus k. Now, we can get k heads and n minus k tails in any order. So how many combinations are there? That is this. combination, this many combinations. So we just multiply these occurrences with this probability, and we get this probability function. Okay, so we say this random variable k follows a binomial distribution, and we write like binomial distribution with parameters n and p. Okay, in this case there are two parameters. P is the probability of getting ahead in one flip, and n is the number of flips in total. Okay, so for different n and p, we have this kind of histogram or relative frequencies. Okay, this is the value of k. Okay, this is the value of k. So when n is 10 and p is 0.5, we have this purple line. Okay, so it's if you look carefully, this looks symmetric around 5. Okay, so this probability is equal to this probability. So k equal to 0 and k equal to 10, they have the same probability. Because in each flip we have the equal probability for getting a head or getting a tail. Okay, and the maximum probability is obtained when k is equal to 5. Okay, now let's increase the number of flips to 20 and keep the probability to 0.5. Then we have, let's see, we have this green line like this. Okay, the probability for k equal to 1 up to 3 are almost negligible, and also for this one from 20 down to about 18 or 17, those probabilities are very small. And the maximum probability is obtained when k is equal to 10, and this distribution is symmetric around 10. Okay, and now consider the case where the probability of obtaining heads and tails are not equal. So n is 20 and p is 0.1. So the probability of getting a head is very small. In that case, we have this distribution. Okay, and it's supposed to go up to here. Okay, now it's not symmetric at all. The maximum probability is obtained at, I think it's 1, 2, 3. So k equal to 3, I guess. And since the probability of obtaining a head in each flip is so small that in total there are about 3 or 4, maybe 5 or 6 heads. Those heads, number of heads are obtained with non-negligible probabilities. But for high number of k's, the probabilities are very small. Okay. In contrast, when the probability of obtaining a head is big, then we have a distribution set like this, shifted, biased towards higher values of k. Okay. So let's study some properties of binomial distribution. First of all, its expectation value is np. So n is this random variable, this parameter, and p is this parameter, probability. And the variance of k is given by n p 1 minus p, which is n p q. Okay. So just use the definition of k. Definition of the expectation values and variance, you can actually calculate these values. But when we studied probability generating function, we show that if one random variable is a sum of independent random variables, its probability generating function is a product of probability generating functions of all those random variables that comprise the sum. So in this case, in each flip, oh, not this one, each coin flip here, each of these head or tail, this is a Bernoulli random variable. Okay, and the number of heads in total is the sum of all those random variables. Okay, so x1, x2, and so on up to xn. So k is obtained as a sum of all these random variables. So let's see. If we write x1, x2, xn as Bernoulli random variables, so they have with parameter p. Okay, all of them follows the same Bernoulli distribution with parameter p. Okay, then if k follows binomial distribution with parameters n and p, that means k can be expressed as the sum of these Bernoulli random variables. Right? So if x1 is 1, that means a head. If x1 is 0, that means it's a tail. So if you add all the ones here, and zeros are just zeros, so the sum will represent the number of heads in n flips. So that is the binomial random variable. Okay, so if we calculate the probability generating function of k, then that is the product of probability generating functions of all these Bernoulli random variables. But they all follow the same distribution, so these all follow the same distribution with the parameter p, and the probability generating function for a Bernoulli random variable is, we derived this before, that was, what is it, q plus ps. So this appears n times, so it will be power of n. So this should be the probability generating function of this random variable k. So if we differentiate this with respect to s, we have n qps n to the power of n minus 1, power of n minus 1. Then if we put s equal to 1, then we have n q plus p. Oh, sorry, there should be p here, because if we apply chain rule, as ps differentiated with s, so p will remain here. So that's p and p. But p plus q is 1, because the definition of q was 1 minus p. So this is 1. So the result is np. Okay. And if we differentiate the generating function twice, so differentiate this again, we have n minus 1 q ps n minus 2 p squared. Okay, so if we put s equal to 1, what we have is n minus 1, and this is again 1, so we have p squared. So the variance of k is given by second derivative plus the first derivative minus the square of the first derivative. So that is n minus 1p squared, and what was it? This one plus np and n squared p squared. Okay, so let's expand this. N squared p squared minus n p squared plus np minus n squared p squared. This will cancel. This will cancel this. So we have an np and np here. np 1 minus p, which is npq. So this should be the variance of k. Okay. But now, again, compare these results with the case of the Bernoulli variable. You know, each x here, x1, x2, up to xn, their expectation value, let's say xi, is p. And their variance of any of xi's, is pq. Remember? This was the result obtained for the Bernoulli random variables. So if you compare these results with these results, let's see, this and this, you see this is just n times the expectation value of the Bernoulli variable, right? And the variance also, this is just n times the variance of the Bernoulli random variable. So this is the property of the binomial distribution. Okay, so we can summarize this in a theorem. So if x1, x2, xn, they follow Bernoulli distribution with parameter p. Then if we define a new random variable by the sum of these, and then this sum follows a binomial distribution with parameter n and p. Okay. Let's see another example of a binomial distribution. Let's see. Okay, this is an interesting example. The number of boys in families containing 8 children. So this is old data, say 19th century. So at that time, people had many kids. So in a family that has 8 children, what is the number of boys? What is the distribution of the number of boys? Okay. Each child is either a boy or a girl. So the probability that any children is a boy is given by P. Okay. And so boy. And the probability that a child is a girl is Q. Okay. So the total number of boys follows a binomial distribution. Okay, so number of boys can vary from 0 to 8. Okay, 0 means 8 children. Out of 8 children, all are girls. And 8 means out of 8 children, all are boys. Okay, by appropriately choosing the value of P, value of P, we can actually predict the distribution. Okay, probability of you know distribution of number of boys. So if we so in this study they studied 53,680 families. Okay, out of these families, 215 families had no boys, and 342 families had 8 boys. Okay, and 14,959 families had 4 boys, and so on. Okay, if we choose a right value for P, we can approximate this distribution theoretically based on the binomial distribution. Okay, in binomial distribution, the probability that there are no boys is given by Q to the power of 8. Okay, and if you multiply this number by the total number of families, you can predict the number of families with no boys. Okay. Again, also according to the binomial distribution, the probability that there is one boy out of 8 children is given by this. Okay. So this P is one boy. Q to the power of 7 means 7 are girls. And this 8 comes from the combination. So 8 out 1 and 7, so that is 8. Okay. So and so on. So 28 should be 8, choose 2. So okay, but so this binomial distribution n and p, n is given as 8. Okay, 8 children. So what is p? Actually, p is not 0.5, it is 0.5147. Okay. So that means the probability that a boy, uh, a, that a child is a boy, is a little bit more than 0.5. So it's not equal. Actually, this is a very interesting observation, and it is universally observed. So anywhere in the world, the probability that a child is a boy is higher than that of girls. And there are many explanations for that. Uh, Usually boys are not so strong and they tend to die early. So nature has molded humans to bear more boys to begin with. Probably. Okay. That was binomial distribution.